Jogamin, AP Physics, energy lesson, my computer black screen, blue screen in fact, and it's ruined 14 minutes of this. Now to do this again, so I'll try to do this faster this time because it was actually running out of time. So we're gonna quantum lock in like this, and we're gonna talk about physics. Quantum lock in. Alright, we got quantum locked in. So energy, or rather first work. What is work? Well, you may know, learn from AP Classroom, FD cosine theta first. I do not like this definition being given first because it's quite misleading. And in fact, if I were to tell you work equals 0, what do you get out of this equation? In terms of energy, of course. There is nothing you can get out of this equation given FD cosine theta. It simply means nothing. You cannot get anything out of this, so that's why I don't like showing it. I mean, not showing it to be. It's not a good idea to show people that before actual energy. Now, let's talk about energy. Energy, or more specifically, the type of energy we're going to talk about is mechanical energy. Mechanical energy is kinetic energy, potential energy from gravitational potential of Earth, and potential energy of a spring. These are the only 3 energies you're gonna be dealing with in terms of mechanics, and you are taking AP Physics 1, which is on mechanical physics. So these are the 3 energies you will be directly using. There are other energies like sound, heat, friction. Well, technically friction isn't an energy, but let me just get my example with. And air resistance are types of work or change in energy. You might have heard that work is the change in energy. While FD cosine theta is equal to change in E. And FF can be air resistance or friction. And in fact, heat and sound are created, types of energies that are created by air resistance and friction. So that is what the FD cosine theta means. It means a change in energy, undoubtedly, but it is not exactly the energy you think about. And in fact, I'll show you an example. So let's say we had a ball. Let me get a eraser first. So let's say we had a ball on Earth, falling. If you may know, PEG, potential gravitational energy, equals mgh, which, if you had a keen eye, you would realize it is this is derived from FD, which is gravity times height. Yeah, so if you had a keen eye, you can derive this equation pretty easily. But regardless, the energy of this ball at this moment is mgh. The floor is h away from where the ball is at. And let's say there's some air resistance right here. Mg, or when how should I say this? In fact, there's air resistance all around. So when the ball falls down, this is not mgh no more, because remember that g comes from the f over m, fg over m. Remember that this is supposed to be a equals f over m, right? So the acceleration, now that there's fy over m equals acceleration, air resistance, as we know, like friction, reduces forces, which in turn reduces acceleration, which in turn reduces speed. So would the energy now be different or the same if there was a ball that had at the same height dropped without air resistance? The answer is there is a difference. And the difference would be the acceleration is different, so the magnitude of acceleration is its difference. And this mgh will no longer be g, it would be some other number. Actually, no, yeah. But it's hard to explain this when you only know FD cosine theta. That's what I'm talking about. It's hard to really truly explain this without FD cosine theta. And in fact, work. Let me just tell you, work doesn't have a formal type of definition. Let's just say. You may think work equals change in energy or FD cosine theta, which is true, but I'll tell you there's some nuance to that, and that change in E can be so many different things. Now let me draw a tree graph for you. It could mean energy F minus EI. Well, I mean that's simply what delta E equals, and you know what EF can equal? Or these two in fact can equal change in PE plus change in G plus PES plus change in KE. And you know what this could be? PEG in final minus initial. Oh my god, that's a lot. Splingo, oh, oh, oh. Flamingo, oh, oh. There you go. This can literally be work, or it can be less than this. Work can simply just be 1/2 mv squared, which I hope you know is kinetic energy, which is also, I will preface and very much you should know that energy is very much connected to all the units you have learned so far, like extremely connected. Like you may have thought kinematics and forces were like connected because of acceleration. Well, this is literally like energy itself is connected to every unit you know, and it will actually turn like in circles. Like you'll loop back on your previous units while working on energy problems because it's that intertwined. Because most of the energy, because energy isn't a real like physical quantity, so you derive energy from kinematics and forces and whatever that you learned in the previous past. So that is why energy, when you conceptually, you have to explain it with other topics because it's derived from those topics. Also, I must preface that you were working with vector values, like velocity is a vector value, force is a vector value, whatever. These are vector values, acceleration vector value. But energy or work actually has no direction. Wait, let me think about that. Right, maybe work has direction. Hold on, let me think about it. Okay, I'm back. Work is not a vector. That cosine theta, well, oops, there is no cosine theta. The FD cosine theta is the only indicator of it's not indicator of direction, or it's an indicator of opposition or being on the same side. It's gonna be hard to explain, but these are what you call scalar values. Let me give you another example of a scalar value. Distance is a scalar value, but position or change in x either or, are both vector values. Why? Because velocity is a vector value, so therefore these should be vector values, right? But distance, it doesn't matter on a graph or like wherever, if you went north, south, east, west, you still went 1 mile and some place. It doesn't matter if you went 1 mile like this or that, whatever. Distance is a scalar no matter where you go. Change in x, position, they're all vectors. It really doesn't matter where you go. If you have a vector of changing a position going this way and going this way, going exactly back to here. Like, let's say you went here and then you went back. Your velocity and your position will be 0, and your change in x will be 0. But your distance would actually be double of this direction. Okay, that's the difference between velocity and distance and the scalar. Money is a scalar, because negative money means you're losing money, and because of this difference, a negative energy or work means a loss in energy, or a negative change in energy, a loss in energy. While if it was a vector, it would simply mean other direction if it was negative. But energy, even though 1/2 mv squared is in the thing and it's a vector, because it's squared, it no longer has its vector value, because, you know, vectors, you can't, if negative, there can't be no negative from absolute value, it can't be a vector, because this direction does matter for vectors. So that's a key difference. Energy, work, whatever, scalars, these are vectors. So what does it mean to be a scalar, like physically? Well, it just simply means direction doesn't matter, and I'll get to why that matters, but I forgot where I was going with this. But okay, so all I was saying is the nuance of work, change, and E. Work can be so many things. It could be FD cosine theta, it could be MGH, it can be kx squared 1/2. And if you don't know where this comes from or what this is, it's the spring. And also, I know Gary probably didn't teach you this, but a spring, the force of a spring is negative kx, and that's how you get kx squared. Okay, so it could be this, or it can also be MGH minus 1/2 mv squared. It could be so much things. It can, like, let me just tell you this. Although I'm saying work does have no equation, the real equation of work is simply this. This is the real equation. This is the only equation you should think about work. Given, and notice the difference when I say this, given that work is 0, or work or energy is conserved. Conservation of energy means no work has been done on the system. And what that means, system, just means a group of objects. Like an object with Earth can be in one system. And when I talked about air resistance earlier, that is outside the system. I mean, we could put it in the system, but typically speaking, air and friction are outside the system. We don't typically count it in the system. But also, systems aren't exactly like, systems are relative. Like, you don't have to include Earth with this system of objects. If you exclude Earth, the gravitational pull of Earth will actually be work. That's why I wrote work equals MGH. It could actually be Earth. Earth could actually be not a work that is in a non-conserved system. Now, a conserved system means energy is conserved, meaning no energy is lost or gained. I'll go over that later. But let's just say air is work, change in energy, in a perfectly normal system of objects on Earth, where ball was falling and there's air. All of a sudden, now that there's air, there is a change in work. I mean, change in energy. Right? So much to talk about. Yeah. I'm back on talking about conserved energy and energy conservation. When energy is conserved, like I said, when the system is conserved, therefore energy is conserved in the system, work has no change, there's no change in energy, so therefore work is 0. And that's why I talked about in the beginning of the video, what does FD cosine equals 0 even mean? There is no meaning to this. This does not give you anything. But you know what happens when you set work to 0? You get this equals 0. And you know what that equals? EI equals EF. And you probably want to write this down on FRQs. EI equals EF. And EI equals EF. Well, now it can split into whatever the energies in the system happen to be. If there's kinetic energy, if there's potential gravitational energy, if there's spring energy, I mean, these are the initials and there's the final. What determines a final and initial? Typically is its max. The final should be an object's maximum energy of its particular type. And what I mean by this is typically a falling object, right? A ball at raised height and falls has potential energy initially. Its initial is mgh, right? And then when it goes to the floor right here, it has kinetic, the only, and it's not moving from the start, by the way. And then from here, now that it has like 0 distance height, h is 0, so well, where's h? And also since there's no spring, we have took those 0, and FPEG equals that, KEI is that, so all you're left with KEF minus PEGI, and yeah, KE or 1/2 mg squared equals mgh. There you go. This, the very bottom is it is that. And that's what I'm talking about. Like, if you got work equals 0, how are you supposed to get any of this for FD cosine theta? But anyways, M cancel out. Depending on what you're solving, you solve for something. I mean, yeah, you just solve for one of velocity or height, and there you go. You're typically going to be solving for velocity, by the way. Yeah. So, that's basics of energy. It's a lot to energy. It's just a lot, but I mean, you get used to it. Just know that, like, you're always given if there's like a height, or there's a moving object, or there's a spring. It's really simple, really. Also, by the way, let's go back to my air resistant problem, where there was air resistant in a ball. Okay, let's write an equation for that. Well, like I said, air is a change in energy. It's a force outside the system, let's say. So that means it makes a non-conservational force, meaning the system is no longer conserved in energy when interacting with air. Therefore, work does exist. And you know what happens when work exists? You can still write this equation out, even with work. So realistically, work, or especially for this situation, it's simply PKEF minus mgh. That's simply it. Now, obviously, since there's work, this KEF is no longer the same KEF when it didn't have, all that, but it does obviously have the same mgh, so therefore velocity did change. But let's say we did know what the air resistance was. So now air resistance would just be Fd cosine theta plus mgh equals KEF. And you can solve for velocity or whatever you're probably trying to do. So there. That's how Fd cosine theta works and plays into energy. But I don't get why College Board would teach you that before you even learn KEF and MGH. So yeah. I also want to go quickly over the relationship between potential energy and hold on. Oops. Potential energy with kinetic energy. I want to talk about the relationship. As we all know, the typical example, PEI. Let's say a dropping ball again. No, ignore air resistance, error. This is a PEI, and let's say it's filled to the brim. It's the most PEI can have because it's at its max height. And we have KE, and this is how you're gonna draw a quote-unquote low model. I don't know. I never used it, but whatever. KEF or KEI, let's say, because KEI equal PEF plus KEF is the conservation of energy equation, and when there's work, this is the equation with work. When there is a non-conservative force, but when forces are gone, those forces are gone, like in this example, this is typically the equation you're going to use. And KEI is actually 0 because we're starting from free fall and 0, so 0. Okay, and afterwards, at the end, there is no height, no PEF. I guess draw it under. There's none, and there's maximum KEF. Notice how the one switched. But let's say I wanted to find the kinetic energy at height h over 2. H over 2. What would I see? Well, you would actually see that the potential energy would be halved, as you may assume, while also, now that it's speeding downwards, the kinetic energy is also halved. And the relationship between kinetic and potential are like oscillators. Like, as one goes down, the other one goes up. This one goes up, this one goes down. Like, it reduces, it's better to show you, like, for graphically speaking, this is what they both look like simultaneously. Let's say the graph of kinetic energy is red. So, and it would be start at 0, so it's like a sine function, right? And potential energy is cosine because it started from somewhere. And it's basically like its derivative in a sense. Basically, the cosine and sine derivative are the relationship between these two, although I might be mistaken, because the maximum of kinetic energy is the lowest of potential energy, and vice versa. And when kinetic energy is 1/3 of the total energy, potential energy will be 2/3 of the total energy, and so on. That's why I think of it as a derivative of cosine and sine, because they're very closely related to each other. You know? So it basically looks like a derivative, two derivatives graphed together, and this graph would more make sense if this was PES, a spring, like imagine you had a spring, like a little spring, and a hook onto a block, and it was like, and the block was like, it's going back and forth, you know? This is what the graph would look like. as velocity goes towards the thing, the velocity or kinetic energy will reduce to 0, while PS will be at its greatest because it's not moving, and yeah, so forth. It's basically calculus, very very in tune with physics, and it's easy to explain these type of concepts with calculus. Now, at the end of this video, we're at the end. For all I have to say, I want to give you a question, a thinker question based on what I've given you, because I feel like based on what I've already told you, you can probably figure out this problem. Okay, here's my question. Also, I think I forgot to tell you, or at least I meant to remind you, that energy has no direction, per se. There's only the loss of energy, and there's the gain of energy, or no gain or loss. And what that specifically means, though, in terms of physics, or physical quantities, is that, no matter how far you go, okay, no matter how far you go, wait, hold on, I can't think right now with this one. Okay, I gather my thoughts. Okay, so, let's say I went, let's get an arbitrary example. A box went to this position like this. Like, this is the same block, by the way, but, like, drawing it, like, it went that way, right? But then what about if the block went, like, all the way like this? Like, it's this, I'm drawing the path, by the way. I should probably draw it a different color, but, like, and it goes back to here. The thing about energy, although the path is different, like this, the energy, all that matters in terms of energy is that as long as it's at the same place as the normal path, quote unquote, normal path, it will have the same amount of energy, same everything. So, me going from one straight line versus going down, like, if I slid down the stairs versus walked down the stairs, like, I still have the same velocity, and MGH, still the same MGH. Like, let's say the floor is all the way down here, H, and there's a distance L, right? Me traveling down to this step, whatever this step height is, no matter if I jump down it like this, walk down one by one, if I don't know, like, just, like, if I did that, as long as I get to this position, my kinetic energy is the same for whatever way I got to here. My energy is the same thing for how, yeah, my energy is simply the same no matter how I got here. It's simply the same. So, given that, really kind of too long of an explanation of what that should have been, I want you to answer this question. Given two different slopes where one is curved like this, while yeah, and this red slope right here just shows that they're the same triangle technically, with the same angle and the same length and height. Just one is curvy in actual path and one straight line in path. Tell me which one, well, first of all, tell me which one will have the greater velocity and greatest kinetic and velocity. Sure, kinetic energy, velocity starts at the same place and the same place, same energy. But tell me which one has the which has the greatest velocity. Give me 3 seconds. Okay, 3 seconds are now up. Tell you what, you should have answered and said they have the same velocity because they start at the same height and there's the same length of ramp, and also the angle is the same, whatever, but that doesn't matter for now. But they got to the same position technically. They all went down 1H, for both sides. So technically speaking, the velocity on both sides should equal, given there's no air resistance or friction, of course. So now that you answered that question though, it has the same velocity, the same height and length. Here's the money shot question. Which block gets down the fastest? And give your explanation. I'll wait. I am back from waiting. And I'll tell you what. You have you have 3 choices. It's either this, ramp 1, ramp 2, or both will reach the end at the same time. I'll tell you what. The answer might shock you. Because if you picked ramp 1, you're wrong. But if you picked both, you're wrong again. But not only that, you failed kinematics. The answer was ramp 2. Now, why was it ramp 2? Well, like I said, you failed kinematics if you picked both. But also, if you pick ramp 1, there's some potential reasoning, but not really. Also, I think I gave it away when I showed you this line, why it's ramp 2, because even though they have the same energy at the end, same kinetic energy at the end, one got here faster than this one. Why? Because of the slope. And this is where calculus comes in. Well, technically you're doing algebraic physics, and you're not gonna really care about the acceleration of the slope of the ramp and stuff. But let me just tell you. These ramps, the path represents its velocity as a graph. You might be astonished to see that, to hear that, but as you may know, an accelerating body, a uniform accelerating body, like the example here, which is uniformly accelerating due to gravity, the graph of the thing would look like this, x to t, it looks something like that, and velocity will actually look kind of like this, actually, yeah, because it's increasing. Actually, if we're graphing height, y to look something like that, and therefore by is more like the slope as we see here. And actually, let's start right here. Actually, my bad. Let's start right here. And acceleration will look like acceleration y will look like right here. And I'm not gonna draw the y graph for whatever this is. I don't even know what that looks like. Actually, it probably looks like a cosine graph, but it would actually look, the velocity to time graph would actually look like, well, like I said. And if we graphed both these velocities at the same time, we'll realize that the velocity here, look at that, look at the velocity, I want you to look at it, they are tangent to its peaks. It is tangent to its peak, guys. It is tangent to its peak. What that means is that, okay, we just explained that one is uniform, one is UAM, and one is not UAM, not UAM. No, this is why calculus is involved in physics, because since it's not UAM, algebra is not going to cut it, and you're going to need the derivative of each single point. You're going to need an equation for the derivative at any given point of this thing. That's why you need calculus for physics. But you're not going to deal with, this is just a conceptual thingy. You're not going to actually solve this equation wise, but this is only a question to like think about what you're doing, what the object's doing. So, because we know that kinetic energy final equals mgh, I'll tell you that if you look at it the broader version, like from here to here, obviously the speeds are going to be the same, but I'll tell you what, if you looked at it from here to here, and then from here to here, let me get a different color actually. Like if you thought of it of like separate peaks, if you thought of it as peaks, you'll see the bigger picture. Actually kind of oxymoronic, kind of paradoxical, that looking closer we'll see the bigger picture. But look, going down, this is h, or let's just arbitrarily call it h over a, I don't know, doesn't matter, h over something. This distance is h over something. So mg, so mg h over equals equals 1/2 mv squared, right? And we know the lower we go, because it's gravity, the more velocity you'll get. So in fact, the equation should be 2gh square root equals v. This is your equation, and as you can see, the more that height decreases, you might think, actually, hold on, let me think. Okay, I gather my thoughts. Alright, so I'm kind of mistaken. That is a true equation, but the distance, we travel the same distance, but the height is not the same. Look, the normal ramp, this is why I drew this, the normal ramp would actually be here, when this guy would be over here, right? And we know that the more height you have left, wait, hold on. Oh yeah, so if we thought about it in a smaller picture, having a shorter height, like if we went from here to here, find the velocity of mgh normal ramp versus mgh curve ramp, h will be bigger than the normal ramp, so that's why the velocity is also greater at this point. And also notice that its max points, the maximum point, well technically it's not maximum, it's actually the minimum point, the slowest this object can go is the same speed as the ramp of the object in uniform motion. Notice that. So it can, so you know how it go up the ramp, you slow down, right? Well, it'll slow down to match the block on this normal line. It will, it's yeah, that's what that means. It will never exceed the height. If it ever exceeded the height, like if the curve was like this, it would most definitely lose all its velocity and be slower than the ramp. But because this ramp is tangent to its max points, and we know that the higher it is, the surface level to the start is much lower, therefore less kinetic energy, therefore less velocity. And you're not gonna prove this using equations, especially in an FRQ like this. You're gonna have to talk about it conceptually. How are you gonna solve this, or explain why this curve got here faster? And you don't even need energy to solve, to explain it. Like I said before, they're intertwined with kinematics and forces. So an easier explanation, in fact, wouldn't use energy. In fact, energy would be the reason why you were misled to the wrong answer. And let's just say that the ratio, the ramp, the reason why this one's faster in time, like has a quicker time, is because the ramp is steeper than that of this, and it's not so steep that it's just straight up falling and gaining no, you know, that it's like a micro projectile motion problem. At that very moment, you're at some certain angle and you're going down, and we know the more the angle of a projectile, like 45 is the golden ratio, or not golden, but the best ratio for, you know, for a thingy to a projectile motion to go fastest up and down. Just like the slope, you don't want your slope to be exactly vertical so you don't go anywhere this way, but you don't want it exactly straight so you're uniform in acceleration. You want a slightly more curved and yeah, it's some more curved graph that has a better ratio of using gravity as its you just want gravity as its main driving force of going slanted down. So if the graph was like this, it definitely would be a lot faster. Maybe even this, as long as the angle, the slight angle of the tangent line decreases, or it's just less than, or actually no, increase in, if it, wait, yeah, if it increases, like the slopes here, the slope here compared to here, or here, it's just not the same. They're not the same. They're not the same. This slope compared to a slope like this, it's just not the same. And we know that a greater angle, because of sine theta, means faster x velocity, or acceleration, therefore velocity. Yeah, that is a mumbo jumbo mess of an explanation, but there you go.